Now that we've had a look at finding compositions of functions, we're going to move on to something called the transitive closure of a relation. First thing we're going to do is introduce the idea of adding ordered pairs, which visually in our directed graph model is like adding arrows. Adding ordered pairs to a relation to give it desired properties. We're going to use that to define the transitive closure of a given relation. And then we're going to do an example of finding the transitive closure of a particular relation given in directed graph form. And finally, we're going to make an observation about transitive closures that didn't seem obvious just from the definition. So you had a couple exercises on previous set of activities. I gave you a relation. I'll show you what the relation is because I'm sure I don't expect you to memorize these things. That asks you to add arrows to make it a partial order. So here was the relation that I gave you in directed graph form. And of course, this is not a partial order. And what we have to do is we have to add some arrows to make sure it has all the properties that we want. So for instance, we want to make sure it's anti-symmetric, right? Well, what that means is we just don't want to have arrows going both ways. We don't want to have two different elements where each one is related in both directions. So that means we just want one-way arrows. That's actually not a problem. All the arrows that we have are one-way. We don't have to worry about the two-way arrows. So it's anti-symmetric just the way it is. So that part's fine. Now, the reflexive is not so fine because we need to add some loops, some arrows of elements pointing to themselves so that every element is related to itself. So there's four arrows that we have to add to make the relation reflexive. And now we also have to make sure to add some additional arrows to make the relation transitive. So once we've added all these arrows, it's going to be anti-symmetric, it's going to be reflexive, it's transitive, and that makes it a partial order. So the general process of what we do is at each step, we add only the arrows absolutely necessary that are demanded to satisfy the desired properties. And then we take a look at it to see if the properties are satisfied. And if not, we keep repeating this process until all the properties are satisfied. At each step, we make sure not to add too many arrows. So for the transitive closure, we do exactly what we did with the previous relation, except we're not worried about making it a partial order. All we're worried about is, does it have the transitive property? And we're going to make as few arrows as possible to make that happen. So the definition of the transitive closure is, well, you start with R, a relation on the set A, and this could literally be any relation between elements in A. The transitive closure of R, and the notation we use for that is R plus, is going to be a transitive relation, but that has the smallest number of ordered pairs possible. That includes all the elements of the original relation. So you take the elements of the original relation and add as few extra arrows as possible to make it transitive. Another way of saying that is it's the smallest transitive relation such that the original relation is a subset of it. So let's go ahead and apply this definition to our original example. So here we have A, B, C, and D. Now we're going to worry about anti-symmetric property. We're not going to worry about the reflexive property. All we're worried about is the transitive property. And how do we do that? Well, remember, the transitive property says if one element is related to a second element and the second element is related to a third element, then the first element is related to the third element. So we want to make sure and apply that reasoning. So, for instance, we have A related to B, we have B related to D, so in order to make it transitive, we need to have A related to D, which means we've got to add an extra arrow between A and D, going from A to D. And then we're going to do the same thing with C, B, and D. C is related to B, B is related to D, so to satisfy the transitive property, we need an arrow from C to D. And then notice that the relation is now transitive no matter what three elements we have. If the first one is related to the second one and the second one is related to the third one, already the arrow between the first one and the third one is drawn. So it's a transitive relation now, so we can stop. All right, so let's find one more transitive closure. That one was kind of easy, right? Just to get us warmed up. This one's going to be a little bit more complicated. First of all, we have an extra vertex, and there's going to be some other things that are a little bit more complex, but we'll find our way through this, right? But we're going to take the same approach that we did before. We're going to look for triples of vertices where we have two arrows that we have to follow. The first one to the second one, and the second one to the third one. So for instance, we have 1 is related to 2, 2 is related to 4. That's going to demand an arrow between 1 and 4. We have 2 is related to 4, 4 is related to 5. That's going to demand an arrow between 2 and 5. And then similarly with 3, 2, and 4. So we need to have 1 pointing to 4, we need 2 pointing to 5, we need 3 pointing to 4 in order to have the transitive property. And so there we add those 3 arrows. Looks great, except it's still not transitive. Even though we added all those things, still not transitive, because in adding those arrows, we actually created some more problems. Well, that's the way it happens sometimes, right? For instance, if I look at that new arrow that I drew between 1 and 4, now we have 1 related to 4 and 4 related to 5, but we don't have an arrow between 1 and 5. And actually, if you look around the other way, there's an arrow between 1 and 2 and an arrow between 2 and 5. That's also demanding an arrow between 1 and 5. So we have this, these new arrows are screaming at us, hey, please draw an arrow between 1 and 5. And, well, okay, we'll add an arrow between 1 and 5. There it is, right? So, and we still have more arrows to draw because now we have an arrow between 3 and 2. And we also have an arrow between 2 and 5 that we have to worry about. So that demands an arrow between 3 and 5. And actually, that's not the only one. We have 3 pointing to 4, pointing to 5. That also is saying, hey, draw an arrow between 3 and 5. And so, yeah, we got to add that arrow. And then, well, after we've done that, our relation is transitive, and so we're done. So the idea is every time you add a new round of arrows, you have to check again that about whether or not you have the transitive property. If you do, you're finished. If not, you add just the arrows that you need to make it transitive. All right, so I want to make another observation that maybe you noticed in the previous example. Maybe you didn't, but let's go ahead and see it. Well, here's our original relation, and here are all the arrows that we get with the transitive closure. Well, one thing you may have noticed is that if we look at the arrows in ours pointing downstream, so if you're thinking about going down a river, 1 might be the beginning of 1 river, it flows into 2, which flows down to 4, which flows down to 5, and similarly 3 flows to 2, flows to 4, flows to 5 downstream. And if you look at all the extra arrows that were drawn, they were all drawn between vertices that were upstream to vertices that were, or elements that were upstream to elements that are downstream. So for instance, you see 1 is pointing to 5, and you can go downstream from 1 to 5 in 2 ways. You can go 1 to 2 to 4 to 5. Well, that's actually the only way, right? 1 to 2 to 4 to 5. And you have an arrow between 3 and 4, and that is because you go downstream from 3 to 2 to 4. And the question is this another way of thinking about transitive closure that is equivalent to the original definition? And the answer is yes. So if R is a relation on the set A, then the transitive closure R plus is a set of all ordered pairs AB. And again, when I have an ordered pair AB, that's the same as A pointing to B, such that A and B are connected by a directed path in R. And all I mean by a directed path in R is a path going from A to B where you travel the correct way along arrows. So here's what it's going to look like. You start at A, you travel along an arrow in the correct direction to, say, X1, then travel from X1 to X2 in the correct direction, and you keep traveling down arrows until you get to B. So anytime you have some arrows that you can follow downstream from one element to the next, then those get connected by another arrow. So I have to draw another arrow from A to B. And that's a theorem that, well, you're going to address in the homework. If you want to see how you're going to organize that proof, this doesn't actually give you in the proof. I don't actually give you a proof in the reading for this transitive closure, but I encourage you to read that part of it just to see how you'd kind of set up the proof for that particular theorem. All right, so now that you've seen some of these examples, seen some of these concepts, I want you to work on the activities for transitive closure on the PDF file included with this video.